Since atoms and molecules are small, there are an almost unbelievable number of them in any sample that we have. It's impossible to count them individually, so we need a way to handle a large quantity of them that is based on actual measurement and leaves us with group values that are easy enough for us to handle. This is where our friend, the mole, will come in. And later, where our other friend, molar mass, comes in, because really, chemists count atomic level particles by weighing them. But more in a bit. We don't mean mole like the animal that digs tunnels under your sod, or even like Professor Molnium or Meg A. Mole, the mascots for the American Chemical Society. We mean mole like a large grouping of particles defined as Avogadro's number, named after everyone's second favorite counter and potential Harry Potter villain, Lorenzo Romano Amadeo Carlo Avogadro. You cannot make up a name like that. We'll elaborate on the number itself in a minute, but first, let's make sure why we understand why it's necessary. When we measure things, we do so by counting or determining the volume or mass of things that we need measured. Whether one method wins over another is often determined by which of them is easier to do with the thing being measured. For instance, if I was cooking red beans and rice for a crowd, I probably wouldn't count the individual beans, and I definitely wouldn't count each single grain of rice. Both pieces would be too small to make that practical. Instead, I'd probably reach for the 2-pound bag of Camellia brand red beans, which has been measured by mass. And I'd probably put 5 cups of rice in my rice cooker because volume is the better play there. Instead of worrying about how many individual beans or rice grains I end up with, I worry instead about a grouping of beans or a groupings of rice based on the bigger measurement. Keep in mind that even though I probably wouldn't, I could figure out how many beans I have in that 2 pounds if I knew the mass of a single bean. We will treat our chemical samples very similarly. We know the mass of the whole and the mass of the pieces, we can get to the individual count. One more real-world example to show what the mole is meant to do. Here, I have some eggs. How many? Doesn't really matter because I'm more worried about how many groupings I'll end up with than how many individual eggs there are. The common grouping for eggs is the dozen. If 12 of these individual eggs are placed in a carton, they start to become easier for me to count. Eventually, I group all of the eggs into even dozens until I can't do that anymore. Here I have 6 dozen eggs and an extra half dozen left over. The process of grouping moles is pretty similar. Only your atoms are too small to see with the naked eye, and there are more of them than we can think about, so the cart needs to be pretty darn large to hold a whole lot of them. And it's going to be a pretty rare occurrence if we end up with an exact even number of moles. That's a thing that's reserved for general chemistry practice problems. In the real world, we'll have a fraction of a mole, just like we had a fraction of a dozen here, represented by these leftover eggs. The relationship between mass and count becomes more and more important the smaller your pieces get. And since it doesn't get much smaller than our atoms, it should make a lot of sense that the chemist uses the relationship between mass and count pretty extensively. Instead of groupings like the 2-pound bag or the cup or even the dozen, the chemist uses a grouping called the mole. The mole, or Avogadro's number, was originally defined as the number of carbon atoms in a 12-gram sample of pure carbon-12. But since the definition of a gram has been adjusted in the time since that original publication, Avogadro's number is now just defined as 6.022 times 10 to the 23rd units per 1 mole. Know, though, that the original definition indicates that a mole of a substance will have a fixed mass. This fact becomes hugely important as we complete our calculations later. The unit here sounds vague, and that's by design. It allows whoever is doing the measuring to use the unit that best fits their sample. Have a 1 mole sample of pure water? Then cool. You'll have 6.022 times 10 to the 23rd molecules per mole because water is best described as a molecule. Have a 1 mole sample of sodium chloride? Great. Then 6.022 times 10 to the 23rd formula units per mole for you. The sodium and chloride are held together by electrostatic attractions, so molecule doesn't work anymore, and we have to change our unit. Have a 1 mole sample of quackas? Superb! So very many quackas. We would be here for 9.55 times 10 to the 14 decades to get through 6.022 times 10 to the 23rd pictures at this speed. That's bonkers, right? Avogadro's number really is that large. The mole really is too large for human imagination to wrap its head around. So to help put the mole in more concrete concepts, many people before me have developed analogies. It's not important that you memorize these, as they're just for fun and to help illustrate how important it is to come up with some way to count our tiny atoms by a grouping. We now know that Avogadro's number has 2 units associated with it, whatever best describes our sample and the mole. This means that it can be used as a conversion factor to move us from one unit to the other. That process is described better in a separate video. Keep in mind that Avogadro's number is a definition. It's the number of units in exactly 1 mole. This means that the 1 value always goes with the mole unit, and the 6.022 times 10 to the 23rd value always goes with the unit that describes the sample. Used as written here, Avogadro's number would move us from the mole to the unit. Now, I didn't refer to what's in the numerator and denominator specifically because, like all of our conversion factors, Avogadro's number can be inverted to move us in the opposite direction. When used as written here, Avogadro's number moves us from the unit to the mole. Again, all of section 1.4 is mostly quantitative, so even our theory part involves a lot of numbers. We will use the mole in calculations in the next subsection. But for those interested and familiar with dimensional analysis, here is how I came up with that decades value on the earlier Quokka slide. Each picture was set to appear half a second after the last one. If I'm worried about 1 mole of pictures, that leaves me with 3.011 times 10 to the 23rd seconds per 1 mole of pictures. The second is too small a unit here. I know that because of that large positive exponent. So I moved from seconds to days, which still left me with a big exponent. So then I moved to decades, still a big exponent, but now I'm bored and I think you get the point. The process shown here is dimensional analysis. While this was a conversion for something very silly, this kind of thought process is free game for your Module 1 quiz.